This video is kinetic molecular theory, the theory of how molecules can move, or particles. And what we're supposed to do is differentiate between an ideal and a real gas. So first, scientists construct models to explain the behavior of different substances. And a study of behavior of gases have led to a model called the kinetic molecular theory of gases, or KMT. It describes the relationship between pressure, volume, and temperature, velocity, frequency, and the force of the collisions inside the particles of a gas. So the assumptions of this theory are that gases are composed of a large number of particles that are in a constant, random, straight line motion. So they should be going, we can't know where they're going to go, but they're going in straight lines, as you can see in the picture on the bottom of the screen. Straight line until they hit something, straight line until they hit, straight line until they hit. And they collide with other particles or the walls of the container. So you can see them colliding with the particles or the walls by that arrow. The volume of a gas is negligible, meaning that the actual size of the particle is much smaller than the distance between each particle. So the volume of a gas is actually mostly empty space. It's mostly measuring the distance between particles rather than the particles themselves. There's no force of attraction between gas particles. They hit each other and they're elastic, meaning that as soon as they collide, they hit right off like two billiard or pool balls. There's no reason for them to connect. Whereas an inelastic collision, where they would have an attraction, would be if you had like two pieces of really sticky gum or magnets. When they have inelastic, they hit and they stay together. So our gas particles have no attraction to keep them together, and therefore the collisions are elastic. They hit and the energy is transferred but not lost during the collision. Remember that the kinetic molecular theory of gases is theoretical and describes an ideal or perfect behavior of gas, but there is no real gas that behaves exactly like this theoretical model. In real life, real gases, the following factors contribute them to having deviations or differences from the ideal model. Real gases have a small but significant volume, so that would maybe change the volume that we're measuring. They do exist. And the gas particles do exert some attractive forces on each other. There are some particles that like to hover together, which is why we might be able to smell them a little better, than gases that like to spread apart. So we're imagining that those are not important factors to make our calculations easier. So gases behave most ideally if they're under conditions of high temperature and low pressure, because in those cases the particles are moving really fast and they collide more often and there's less chance of them attracting each other because they're just moving too fast. And the particles are farther apart from one another. When they move really fast, they spread apart. And so if they're moving really far apart, again, they can't attract each other very well. As they get closer together, they're going to start to attract each other more because they're in a confined space and they won't be able to move as much. And so the summary gases deviate or stray from that in the opposite conditions. So our real gases, if they're cold with high pressure, they'll move slower and they'll get closer together, which would be that they do easily attract each other. So the summary of ideal versus real gases. A perfect gas is imaginary, and a real gas is our actual gas that we work with in a lab. The ideal gas follows the gas laws we're about to do in the next few videos, whereas real gases don't follow gas laws exactly, but it's a good approximation. Ideal gases, the particles are not attracted to each other at all. In real life, particles do attract each other a little, but we're going to try and ignore that to make it easier for our calculations. We won't be able to ignore those in AP and college level classes. In ideal gases, particles have no volume. The particles themselves, we're ignoring them. We're just measuring the distance between them. But in real life, the particles have some volume. They do have a radius. They do have some space. We're going to ignore those. In ideal gases, the particles move in straight line motion. And that's true for real gases. They do move mostly in straight lines, but sometimes they can be curved by looking like they curve because they can be bombarding into other things. And ideal gases have elastic collisions. They transfer energy, but energy is not lost or gained. In real life, we have things like friction that take away some of the energy, but we're going to ignore that. So an example, under which conditions of temperature and pressure would a gas behave most like an ideal gas? And so we're saying we want them to spread out so that they don't attract each other, and we don't want them to be too close together. So I picked the choice where it was hot to spread them out and not pushing, low pressure. Gas pressure was a force that exerted on a container of the container walls by the particles of the gas, and we use kilopascals and atmospheres to measure them. Our standard pressure is one where we had 101.3 kilopascals or 1 atmosphere. Sometimes we also talk about 760 millimeters of mercury. And the standard temperature now that we're adding in is 273 Kelvin, or pretty cold, 0 degrees Celsius, where water freezes. In these conditions, this is what we're saying some of the labs are going to be concerned. It's kind of cold, so the particles might be a little closer together. It'd be better if the gases are farther apart at room temperature or even hotter. So here's another example. An assumption of kinetic theory of gases is that the particles of a gas have, and the choice that I picked was that they should have a little attraction for each other. They should be hitting and moving right away, and an insignificant volume, because in that case, we're actually measuring the space between them and not the particles themselves. At this place, you should be able to differentiate between ideal and real gases.